Hello again, class. We've done two important topics in chapter 7, and we are in week 6 still. So, the two topics of importance were defining the basic gain cell and looking at the cascode method to improve gain and output resistance of the gain cell. So, the next important topic is actually a collection of topics in our textbook, all under item 7.4 or section 7.4. And this section is called IC biasing, and it does a little more. We've already used some of these ideas, but here we really try to understand what exactly is a current source, what are current mirrors and current steering circuits. Okay, so that's 7.4. So within 7.4 we have 7.41, which is the basic MOSFET current source, MOSFET current steering circuits, and this includes current mirrors also. And then the same three things we learn about or as applied to BJTs in 7.4.3. Okay, all right. So with that introduction and this recording, I'll just do the theory of this, and the next we'll do numerical examples and problems. All right, so that was slide 42. I'll move on to slide 43. So biasing in an IC, right? So you have an IC with hundreds of amplifiers and other circuits, and you need stable current values, IDs basically, drain currents, that you can then apply everywhere. So instead of having to generate these and use a large number of resistors, as we just studied, uh, it's preferable to use current sources which are easier to implement on an IC than creating resistors. So the approach then is to at least have one good reference current available, and to do that you need a very high precision resistor. So maybe in a circuit with one or two integrated circuits on a board, you put a high precision resistance with very low tolerance outside on the board. Okay, and using that one reference and a nice high precision source, voltage source, VDD, you then create one current which you know is absolutely always will be stable, is not subject to too much variation because of changes in temperature or with load. So one such current is generally first has to be made available. So that current, an accurate DC current called a reference current, I reference, is generated at one location using a transistor and a precision resistor. So that's step one. This I reference is then used to generate a constant current source I/O output from a paired or matched transistor. So you take I reference and then you immediately create another current I0 or I/O. This I/O can then be replicated using current mirrors at various other locations for biasing the various amplifier stages, and this process is known as current steering. You know what steering is? Steering means driving a car, steering a car, right? So you can take this current and take it anywhere else on the IC. So the last step then, or the conclusion, is that multiple bias currents or load currents, sometimes these are bias currents, sometimes these are load currents, they can all thus be created from one reference current. All right, so that was the introduction of the summary of all the steps. Now let's look at some details on each step, and then also how to implement these current mirrors and current steering and so on. So a basic current source creates an output current I output, right? I/O. So the drain current so how do you get this? You get this from this kind of circuit. The circuit has two Qs, Q1 and Q2. In this case, they are both MOSFETs, but there's also BJTs that can do the job. And they are connected in a certain way, right? This is called a diode connected circuit, where you take a MOSFET and the drain is just connected back to the gate. Such a circuit, such a connection is a diode connection. So the drain current of diode connected NMOS device Q1 is supplied by VDD through a precision resistor R, which in most cases would be outside the IC. Okay, so this R is sitting outside. It's a big one. Probably physically the size is almost as big as an IC, and also it's expensive, more expensive than maybe the IC, but it sits outside. So the current generated in Q1's drain, this current, is I reference is VDD minus VGS, right? VDD minus gate to source this voltage of Q1, okay, divided by R. So that gives you the value of the I reference. Now, relating the output current to the reference current, this current then, this is what we are more interested in, right? This current is shown to be connected to I reference through this formula. I output by I reference is the aspect ratio or width by L ratio of 2 divided by 1. Okay, so make sure you understand. This is a bit like our transformer turns ratio, right? Changing currents and voltages on the primary to the secondary. So same idea, the output current divided by input current or reference current is W by L of 2 by W by L of 1. And some of this derivation is in your textbook. Please go through it and get some idea, so you have some idea of how this logic actually comes about or exists. Okay, so this ratio, the current gain or current transfer ratio of the current mirror, so this whole thing is also called a current mirror, okay, which maybe I haven't said anywhere, but this combination is a basic current mirror. So the current gain or current transfer ratio is this. In the special case of identical transistors, that means if the two are the same, I mean W by L of 2 and W by L of 1 are the same, then IO is just I reference, and the circuit simply replicates or duplicates or just copies whatever is here is copied here. So that it simply replicates the reference current in the output terminal, and this is the output terminal. So when we say a current source is giving me I0, what that means is that I0 is coming out from this transistor Q2 at its drain. It's available at its drain. Okay. Now, this may be exactly equal to I reference, or it may be equal to 2 times I reference, or it may equal to half times I reference. We don't care, right? Depending on the aspect ratios, this can be different. But sometimes it's exactly the same as I reference. Okay. But when we say output current or current from a current source, which we have said many times already in the last few lectures, without clearly totally understanding what it is, this is what it is, right? And this is how it is defined. Okay, now one important condition for this to be true and this relationship to hold, Q2 has to operate in saturation. So it's your job as the user of this I0 to ensure that Q2 never leaves saturation. That means the external circuit outside here through which I0 is flowing, that has to ensure that the output voltage here, which is the voltage drained to source, right, and source is grounded, so just drain voltage here, that VO has to always be greater than VGS minus VTN for NMOS transistor, or we can describe that as VO has to be greater than or equal to the overdrive voltage. Okay. So this is a simple version of the formula. In the textbook, then he tells us that if you have to use or include the effect of channel length modulation, which you know is a phenomenon in MOS circuits, and then corresponding to that we have this VA, which is an early voltage. So if you have to include that, then this formula becomes slightly more complicated. Now you have this 1 plus V0 minus VGS by VA2. Okay, so depending on how the problem is given, sometimes they'll say VA is 0 in a problem, then you can ignore this, right? But sometimes it's not 0, then you have to use this formula. Similarly, the output resistance also is an important factor in all amplifiers and circuits, and that is defined as the change in output voltage over the change in output current, which is nothing but RO2, which is the intrinsic output resistance of Q2, which can also be sometimes defined as VA2 by I0. Okay. All right. So here are some examples that we look at. Here, for example, the early voltage VA prime, VA equals VA prime into L, we have seen that also, but VA prime is given as 20 volts. So then you have to use the more complex formula. Sometimes it's not given. Well, here also there's a VA prime. We'll come back to these problems in my next recording. Okay, so moving on. So now we were introduced to how a current source operates and how it creates an output current, right? So how do you then take this one output current and use it exactly the same output current or some proportion of it, right? Double of it or triple of it or half of it or 1/3 of it. How do you take that I0 and use it elsewhere? And that idea is shown here again using current mirrors, right? So we use the current mirror to create an output source current, and we are using current mirrors again to create multiple biasing and load currents. So let's look at this somewhat more complicated circuit, and here this is called a current steering circuit in 725, and I added some things here. So two new output currents, I2 and I5, are available for loads and for bias, right? So first we have one reference current that we know is created through a resistor, blah blah blah. Then we know that one output current can be created from one current mirror consisting of two transistors. But what you see here is we've created another one. So two output currents are available. One is I2, one is I5. Okay. So how is this possible? Well, first you take Q1, Q2, form a current mirror, you get one output current I2. This you know very well. But nothing prevents us from putting a third NMOS transistor in the same connection, right? This and this, the drains are connected. Now you can connect a third transistor also with its drain. And all these negatives in this case are shown to go to another source. So this is a two power supply circuit, right? We have plus VDD and we have minus VSS. DD meaning drain, SS meaning connected to the sources, right, of these NMOS devices. Now, what else have we done? Not only have we introduced this Q3, but the Q3 is now connected to Q4 and Q5, which is one more current mirror. And this I3, remember this I reference, right, for Q1, that then duplicates into I2. Similarly, for this Q4, this I3 behaves like an I reference, right? So this I3 was created from here, but for this mirror pair, Q4 and Q5, the I3 behaves as a mirror, and then you can duplicate the I3's value, which actually I4 is also shown, but I4 equals I3, same thing, right? So you get I5, which is a second current, which is available to go somewhere else into the circuit for other uses. Okay. Now watch that these two are PMOS transistors while these three are NMOS. So basically both are possible, both types of devices, because we know that one of the biggest advantages of MOS technology is CMOS, which means both NMOS and PMOS can be in the same circuit, in the same IC, on the same board. So anything you do, you better do it to cater to both. And so what we see here is both PMOS and NMOS devices can be fed using currents generated by current mirrors and the technique of current steering. Okay. So having said this, let's see. Yeah. Let me read a little bit of this. The source current is replicated using current mirrors at various other locations for biasing the various amplifier stages through a process known as current steering. So current mirrors are formed by NMOS transistor pairs Q1 and Q2, and then also by Q1 and Q3. So what is the value of I2? We have seen this. This is assuming you are ignoring channel width modulation, etc. Simplified version. But I2 is, we've seen this. Similarly, I3 is available. I3 is steered towards another mirror formed by PMOS transistor pair Q4 and Q5. I3 equals I4, right? And this current acts as a second reference. So the first reference is Iref, the second reference is I3 or I4, and then you get the formula for I5, which is this current available to go outside, as I4 times this ratio. Okay, W by L5 over W by L4. So I hope this concept is useful and interesting. Please take a minute to become quite familiar with it, because a lot of the stuff that we do in the remainder of the course will blindly use these ideas that we just studied. Some of this derivation of these formulas are in the chapter, in the textbook. Please take a few minutes to read them and understand the logic, so you have a better overall understanding of the material. Okay. So a note about what are we doing with those new currents, right? We created I2, then we created I5. So application of the constant currents I2 and I5 generated in the previous circuit. So first current I2, right? It's here. So I2 can be used to bias a source follower amplifier. So this is a source follower amplifier, right? Source follower is also called common drain, if you remember. So a source follower amplifier is implemented using Q6, and it needs a bias current, and that bias current is coming from Q2. So that's an application of I2. What about I5, which also we created? So he says I5 can be used as the load current for the common source amplifier, right? So here we have a common source amplifier, which is a basic gain cell, right, with an NMOS type device or a PMOS type. In this case, it's an NMOS type device. So this NMOS device Q7 is a gain cell. It is being used as an amplifier, common source amplifier, and it needs a bias current, right, which normally you would stick a resistor here if it was a discrete circuit, but because it's an IC circuit, you show a current source on top, and that current source is Q phi, which now we know how the Q phi came into existence, right, in the previous slides. So this just tells you that when you create these new currents, they're not for fun or to waste, but to do other things with other amplifiers in the IC. All right. Again, important to remember that all this can only work if saturation conditions are satisfied. That means this output transistor Q2, this output transistor Q5 have to be in saturation regardless of what loads they are connected to. So what we are saying is saturation operating conditions. To ensure operation in the saturation region, the voltages at the drains of NMOS Q2 and Q5, well, first Q2 and Q3, okay? Q2 and Q3 are constrained as follows. That means the voltage at the drains of 2 and 3, they have to be greater than or equal to. So as I told you, this is a double power supply circuit, right? Not just VDD, but we also have minus VSS. That means you can operate many more devices using, if you have two power supplies, it's better than one. But normally if we didn't have it, we would just say V drain has to be greater than or equal to VGS minus VTN, right? You saw that before. But because minus VSS exists, you have to stick that also in the formula. And then the formula for the drain voltage, that means the voltage at this point, V2, or the voltage at this point, VD3, VD2, VD3, they have to be greater than or equal to not only VGS minus VTN, but also minus VSS, right? And why do we say VGS1? Because the same VGS1 that came from Q1 also applies to Q2 and Q3, right? Because they're all connected to the same point. So whatever voltage exists here, and exists here between gate and source of Q1, Q2, Q3. Okay? So the drains of Q2 and Q3 will have to remain higher than minus VSS by at least the overdrive voltage. So what this is just saying what this is in words. Similarly, you need to keep Q5 in saturation, and remember this is a PMOS, so the relationship is slightly different. It has to do more with VDD here. So VD5, the voltage here, has to be less than or equal to VDD minus the absolute value of VOV5. Okay? And here VOV5 depends on VSG5, which is different from VGS1. Okay? So VOV5 would be VGS5 minus VTP, right? For P, for the PMOS. So whatever it is, this condition has to be satisfied. So bottom line is this transistor, this transistor, this transistor, they have to be in saturation. Otherwise your current source may not work very well. Okay, before we move ahead, I had to introduce one new idea. Maybe it's not new, maybe you know it, but the idea of current source and current sink. And it wasn't too clearly mentioned in the chapter, so I thought I'd go and find some information from somewhere else and help you understand the idea of a current source and a current sink. So here's this big device, right? Big blue box. So is the blue box a current source or is it a current sink? Okay, that's the question. So you're asking me, I'm asking you, do you know, right? Is this device a current source or a current sink? How can you look at a circuit and say, if something is a source or a sink. A source is like your tap of water, right? Water comes out of the tap. A sink is where in your wash basin in your bathroom, after you wash your mouth, the water goes down the hole. That hole is a sink. So, how do you define a device to be either a source or a sink? So, in this configuration, this device is connected to the battery, the current, and then the load is connected to the output of the device. So, the current comes through the device, and then goes to ground. So, current flows out of device. So, when a load is connected to a device, so that the device supplies current to the load, then the device is said to be a current source. Let's look at the opposite. The connection here is slightly different. The device is still connected to the power supply. It has to operate, so it needs plus and minus. But the load is also directly connected to the power supply. So the current begins to flow from the positive terminal of the power supply down through the load and then enters the device and then goes out to ground. So you see the difference in how the current is flowing. Here it first flows through the device, then the load. Here it first flows through the load, then the device. In this connection, this device is operating or working as a current sink. So when a load is connected to a device, the device, so that the current flows from the power supply through the load and then into the device, then the device is said to be a current sink. Okay, so understand the difference between source and sink, because this terminology starts to appear in our circuits business. Okay, well, in our section 4.2 business. All right, so Q2 and Q5 have become the sources of currents, right? So far we have said Q2 is creating a nice current, Q5 is creating a nice current, I5, right? So we have said Q2 and Q5 have become the sources or creators of current I2 and I5. Now, here's another way in the textbook he describes it, the writer describes what is happening. Q5, this Q5, is pushing its current I5 into a circuit. On the other hand, Q2 is pulling its current I2 from a circuit, right? So there's a circuit here and Q2 is pulling it, while here you can think of Q5 as pushing it into this circuit. Okay, now these words are from the textbook, I didn't put them there. So based on the idea of Q5 pushing something, he says Q5 can be called a source, right? Similarly, the idea that Q2 is pulling something, or it's the current is first flowing through the load and then entering into the Q2, we can call Q2 a current sink. So many times in circuits you're going to see the use of the words source and sink for transistors and circuits, smaller sub-circuits, and you must understand what we're talking about. So I hope this helps. Here's an easier rule. NMOS circuits are generally used to implement current sinks. So this is NMOS and it's a sink. PMOS circuits are used to implement current sources. So here's a PMOS device and that is becoming a source. So here's a source, here's a sink. I don't know what that is. Sorry. I think it just came mysteriously. All right. So you see this load business I added. It was not in the original drawing, in this drawing 7.25. But I hope with this and this previous slide 51, so slides 51 and 52 give you a good understanding of what current sources and current sinks are all about. Okay? All right. So we've learned steering circuits, we've learned current mirrors. There are more problems. Many of the problems are about the same circuit that we've already discussed quite a bit, the theory. So here is an actual exercise 716 from the textbook where we will go through and look at an actual numerical with a current, sorry, yeah, with MOS current sinking circuit. All right, another one. This is slightly different, different problem. It still has the same 405 transistors, but it's laid out differently. I don't know how different it is. Oh yeah, so these are NMOS here connected to the I reference. Here we have PMOS connected to the reference, right? So slightly different, but same logic, and we'll come back to that later. One last thing, and then we'll move on to BJTs. VCS minimum denotes the minimum voltage needed across the current source or sink for its proper operation. So what should the current source or sink voltage be? Minimum voltage, so that they are in saturation. V output here has to be less than VDD minus VCS minimum, where VCS denotes the minimum voltage. Similarly, this is for a current source, this is for a current sink. V output has to be greater than or equal to minus VSS plus this VCS minimum. So we've already seen these same formula in slightly different form, right? This is for a sink, this is for a source. So that's what he is again written here. Yeah, here there's a plus OV, here there's a minus VOV, right? And those same two format of the formula appears here. So whatever is after this VDD or after this VSS has this name he is given, VCS minimum. Okay. All right. We have to move on to BJT circuits. So many of the ideas we have studied, obviously they apply to BJTs. Although, at NAU, like I said, at this point, most professors are not studying too much BJT. They've switched over totally almost to MOS. I have another 10 minutes to go, so bear with me while I continue on BJT ideas a little more. But truly looking at how the world of electronics is evolving, because of the great advantages of MOS and CMOS, most amplification circuits and ICs, also even analog circuits, tend to be MOS based technology. So having said that, let's quickly look at BJT circuits. Now the problem with BJT is that this beta is a very variable thing between transistors of the same family, and they can mess things up. For MOS circuits, you know that there is no gate current, so gate all current can be assumed to just flow from drain to source. But with BJTs, um, because drain or not drain, now I should change my terminology, emitter, base and collector. So base is not open, so there is a little bit of base current. But the way in ICs the analysis is proceeding, you can first assume that beta is very high, right? If beta you assume is infinity, then it's almost like saying that my BJT is like a MOS device. There is no base current. So how do you start the analysis of a BJT current mirror? So first of all, current transfer ratio, right? So let's assume that beta is very high, close to infinity, then the formula for this I output, the current source value IO, and the I reference, which is the same thing here, they are related. Remember, for NMOS or MOS devices, we talked about aspect ratio or W by L ratios, right, of the two devices. Here, instead of W by L, we have the area of the emitter base junction. So, area of the emitter base junction here. So, the area of the emitter base junction of Q2 divided by the area of emitter base junction of Q1, that ratio gives you the relationship between the IO and I reference. And in the middle, we also introduce IS2, IS1, which I'm sure you all know what it means, so I don't have to tell you again. But IO by I reference is also sometimes shown as M, or the current transfer ratio, or the current gain. Now, so this formula looks a lot like the NMOS case, and I think you can understand this without me having to talk too much about it. Now, one other important condition before we leave. Remember, the saturation condition, or the condition that a MOS transistor has to operate in saturation, the equivalent condition for BJTs is that the transistor, the NPN or PNP transistor, has to operate in the active mode, right? Saturation there means active here. So the collector voltage V output here, which is the VCE, has to be V emitter plus 0.3, right? Now emitter is already at 0 in this connection. So basically what you want is this VO should be plus 3, right? So the collector voltage is higher than the emitter by 0.3. And we also know this general condition from earlier, that VCE of an NPN transistor has to be greater than 0.3. So the minimum voltage condition for the transistor, for the BJT, NPN BJT, to be in saturation, in active mode, is that this voltage at V0 is above 0.3. Okay. All right. So let's move on to slide 57. Oh, I know you'd forgotten all about IS, right? I told you IS2 by IS1, and I know you know, but in case you don't know, I brought a slide from our chapter 3 notes, semiconductors, where you know that the current in across a junction, PN junction, can be written as I is equal to IS, where this current IS is called the scale current in this form, right? And what is IS? IS is all this complicated stuff. It depends on the area and so many other things, that the length and the D's conductivity, right? Doping levels. Even I have forgotten all that. But Q, of course, the charge of an electron. So IS depends on all this. We don't need to remember all this, but I just thought I'd refresh your memory to say that when you see this IS in the context of a PN junction, you must remember that it plays an important role. In fact, the current at any given point can be written approximately as IS times V by Vt, where V is the applied voltage, Vt is the 225 millivolts, right, constant. Similarly, V for a given I also can be written as Vt natural log I by Is. So Is is an important thing, and that's how it showed up here. And it's proportional to the ratio of two PN junctions. The scale current ratio is proportional to the ratio of the EBJ areas. Okay. All right. So now that was the ideal case with an infinite beta, but we know actual betas lie in the range of 50 to 150 or 50 to 200. So assuming Q1 and Q2 in the circuit are matched, that means on paper they have the same areas for their emitter base junction, but the betas, the the transistor manufacturer tells you, hey, this beta can be 50 to 200, this beta can be 50 to 200. So there's so much uncertainty, right? But you can still use a formula. If this is the case, then this formula applies. Instead of this nice easy formula, right, IO by I reference is this, it now becomes a little more complicated. So we say 1 by, yeah, so this is the formula to use if betas are known. So you use, and if the beta is in this range and Q1 and Q2 are matched, then it's 1 by 1 plus 2 by beta. More general formula where Q1 and Q2 are not necessarily matched, meaning they are not exactly the same EBJ area, but we know that their currents are related by this relationship. IS2 is M times IS1. Then the formula connecting I output to I reference is even more complicated. So M by 1 plus M plus 1 by beta. In general, lower beta results in lower current transfer ratio. So your bias currents are going to start dropping just because you are using BJTs and they have their beta variations and all that. So all this derivation is again in the textbook. Please take a minute and go through it. Okay, same ideas about having to include the early effect, right? So if early effects are given in terms of early voltage VA, then the simple formula of I0 equals I reference this now has another factor that you have to include. And then the output resistance is also defined in terms of early effect in this way. Okay, the output resistance is not infinite anymore, it's finite. All right, so problems, we'll come back later. Similar to BJT circuits or MOS circuits where we then employed the idea of current steering, here also we'll start to look at that. So first of all, you have this circuit, and instead of, first of all, we need to create an I reference, right? So far, I think we've just blindly assumed there is an I reference, but let's say we are given the value of R and VCC, collector voltage. From there, we can create or calculate I reference ourselves as this. Then the output current. So you can call this current mirror a current source now. It's creating an output circuit, output current I0. That output current, as we have already seen, has these values if it's a matched case, right? And then the output resistance. So kind of repeating what we just did, where we introduced the current mirror, but now we see a real resistor and VCC. Okay, now we come to current steering. So this is the more challenging and interesting aspect of BJT circuits. So if you have a dual supply situation where we have a plus VCC and a minus VEE for emitters, then the relation, the I reference calculation has to include both, right? Otherwise you would just say this I reference is this VCC minus the drop here, the emitter to base, and calculate current, right, divided by resistance. But because you have both VCC and VEE, see how we do this calculation. It's actually VCC minus of minus VEE, so the sign of the minus VEE flips to plus, and then the rest of it. So assuming all the transistors have high beta and thus the base currents are negligibly small, neglect the early effect. So with these assumptions, this circuit, we can walk through this and see what is going on. So basically here also, similar to what we did with the MOS steering, we are creating new currents. Okay, So we have one given current I reference, then we are creating I2, then there's I3, I4, right? So some of these are available for usage outside, some are internal, but how this current steering works, I will come back and explain to you in my next recording, and then we'll also do some problems. Okay?